Another example is a 4-pole 50 Hz star-connected alternator has 15 slots per pole, and each slot has 10 conductors. All the conductors of each phase are connected in series, the winding factor being 0.95. When running on low load for a certain flux per pole, the terminal EMF was 1825 volts. If the windings are lap connected as in DC machine, what would be the EMF between the brushes for the same speed and the same flux per pole? So assume sinusoidal distribution of flux. In our problem, we have an alternator which is connected in star, and when we say star, it is in 3-phase. So it has a generated voltage equal to 1825 volts. So that is in 3-phase. And number of pole is 4, frequency is 50, short pitch factor is 1, and distribution factor is 0.95. We have in DC, we will calculate the generated voltage at when your windings are lap. So remember, in your DC generator, lap winding is equal to multiplicity multiplied by the number of pole. So this is our working equation. For the generated voltage in AC, we have 4.44 kpkd, frequency, flux per pole multiplied by the number of turns of conductors. While in DC, we have the generated voltage is equal to number of conductors multiplied by the number of poles times flux per pole times speed divided by 60A. So first, eto given na. We can calculate speed by frequency is equal to Pn over 120. And A here is in lap winding. So ang unknown lang natin dito is the flux. We'll compute this flux in our generated voltage at AC. So our generated voltage at AC, we need the single phase voltage, not the 3-phase. So we will divide this one, 1825 divided by square root of 3 para makuha natin yung per phase voltage. So EG per phase is equal to 1825 divided by square root of 3. So that is 1053.664. So flux per pole now will be 1053.664 divided by 4.44 times 1 times 0.95 times frequency is 50. So what about our number of turns? Diba T is equal to Z over 2. From our formula, Z is equal to 2T. What is the value of our Z conductor? So we have here 10 conductors per slot times 15 slots per pole, and we have number of pole is 4. Para makancel yung slots and pole, matira na lang ay conductors. So our Z will be equal to 10 times 15 times 4. So that is 600. Ang kailangan natin is number of turns. So T is equal to 600 divided by 2. That is 300 turns. And this number of turns, huwag kalimutan na naka 3-phase pa tong mga parameters natin dito. Ang kailangan natin is per phase. So we need to get the number of turns per phase. So T is equal to 300 divided by 3 for 3-phase, okay? So that is equal to 100 turns. So times 100. Our flux per pole now will be equal to 0.04996 flux per pole or Weber. So we will use this one in computing our generated voltage at DC. So EG DC is equal to, solving now the generated voltage in DC. So EG is equal to Zipon divided by 60A. Our number of conductors is 600 times number of pole is 4 times flux per pole is 0.04996. Speed is equal to this one. Frequency is equal to Pn divided by 120. So speed is 50 times 120 divided by 4 equal to 1,500 RPM divided by 60 A. A is MP. So multiplicity is 1. Number of pole is 4. Generated voltage will be equal to 749.4 volts when the generator is DC. When it is in AC, it is equal to 1053.664 volts. We now go to next topic, alternator on no load. So as the load on an alternator is varied, its terminal voltage is also found to vary as in DC generators. So terminal voltage is the output voltage. This variation in terminal voltage is due to the following reasons. So the voltage drop due to armature resistance or RA, voltage drop due to armature leakage reactance XL, and the voltage drop due to armature reaction. So these three factors can vary the output voltage in an alternator. So first is the armature resistance, the drop in armature resistance. The armature resistance per phase RA causes a voltage drop per phase of IRA, which is in phase with the armature current I. However, this voltage drop is practically negligible. So armature leakage reactance. When current flows through the armature conductors, fluxes are set up which do not cross the air gap but take different paths. Such fluxes are known as leakage fluxes. So various types of leakage fluxes are shown in this figure. So this is the drop in your IRA, and as we all know that the drop current, if your load is reactive, it is inductive 90 degrees with respect to the voltage. Okay? So eto siya, this is 90 degrees. IRA, the drop in your armature resistance, and the drop in your inductive reactance. This one. If we add this to the terminal voltage from your formula, back EMF, terminal voltage plus the drop in armature resistance and the drop in your leakage reactance is equal to this back EMF. So this is your current. It is lagging with respect to the voltage. So the leakage flux is practically independent of saturation but is dependent on I and its phase angle with terminal voltage V. This leakage flux sets up an EMF of self-inductance, which is known as the reactance EMF. So this is the reactance EMF, and which is ahead of I by 90 degrees. Hence, armature winding is assumed to possess leakage reactance XL, also known as the Potier reactance or XP, such that voltage drop due to this equals to IXL. As part of the generated EMF, it is used up in overcoming this reactance. So this is now E, this one. Etong E, yun. It is equal to the sum of the terminal voltage V plus I multiplied by RJXL. Okay, so same yung current dito, kaya na-factor out yung I dito. So this fact is illustrated in the vector diagram. So this armature reaction, I posted another video regarding this one para ma-imagine nyo yung mga yung mga factors natin, unity power factor, lagging, and leading power factor affecting the output voltage of an alternator. So next topic, synchronous reactance. From the above discussion, it is clear that for the same field excitation, terminal voltage is decreased from its no load value. So we will denote it as EO to V for a lagging power factor. This is because of the drop due to armature resistance, drop due to leakage reactance, and drop due to armature reaction. So the drop in voltage due to armature reaction may be accounted for by assuming the presence of a fictitious reactance XA in the armature winding. The value of XA is such that IXA represents the voltage drop due to armature reaction. The leakage reactance XL or XP, Potier reactance, and the armature reactance XA may be combined to give the synchronous reactance XS. So our XS will be equal to XL plus XA. Armature fictitious reactance XA and XL or XP, the Potier reactance or the leakage reactance. Therefore, total voltage drop in an alternator under load is equal to IRA, the drop in your armature resistance, plus IXS. Okay, so IXS, this XS is equal to XL plus XA. So this is now the vector diagram of your synchronous. So this is IRA, okay, it is in phase with the current. This is the current, and IXS is the sum of IXL plus IXA. So eto. the sum of IRA plus this one, IXL plus IXA is equal to IJS, or the synchronous impedance. So, terminal voltage plus the drop in your impedance is equal to EO, the no load voltage. This one. So, erase natin to. So, JS or impedance, synchronous impedance is equal to RA plus J XS, where your XS is equal to JXL plus JXA. So, impedance, synchronous impedance is equal to RA plus J XL plus XA. This is the Pottier reactance and the armature reactance, armature resistance. If we add this to the terminal voltage V, this one, plus the drop in your IRA plus IJXL is equal to this voltage E. If we add this 3 IRA plus terminal voltage plus IJS is equal to the no load voltage. Okay? So, surutan nyo lang dito yung vector diagram na. Therefore, the total voltage drop in an alternator under load is IRA plus JIXS is equal to IRA plus JXS is equal to IJS, where JS known as the synchronous impedance of the armature, the word synchronous being used merely as an indication that it refers to the working condition. Hence, we learned that the vector difference between the no load EO and the terminal voltage is equal to IJS. So, vector diagrams of a loaded alternator. Before discussing the diagrams, following symbols should be clearly kept in mind. So, EO is no load EMF, this being the voltage induced in armature in the absence of 3 factors discussed. Hence, it represents the maximum value of the induced EMF. So, E is the load induced EMF. It is induced EMF after allowing for armature reaction. E is vectorially less than EO by IXA. Okay? So, makita ito nga less than ni E kasi wala siyang IXA. So, V is the terminal voltage. It is vectorially less than EO by IJS, or it is vectorially less than E by IZ, where Z is equal to square root of RA squared plus XL squared. It may also be written as ZA. So, I is the armature current per phase, and phi is the load power factor angle. In figure 37.27a, it is shown the case of 4 unity power factor. In B is the lagging power factor, and in C is the leading power factor. All these diagrams apply to one phase or of a 3-phase machine. Diagrams for the other phases can also be drawn similarly. So So in A, as you can see, it has a unity power factor, di ba? In your circuits 1, when the voltage and current are in phase, it is said to be a unity power factor. So our I and V here is in unity power factor. And also the drop in your resistance is in phase with the current kasi they are in phase. And also IXL and IXA is in 90 degrees because they have a inductive reactance. So pag inductive reactance, it is equal to the 90 degrees with respect to the reference. So the sum of your XL, IXL, and IXA is equal to IXS. The sum of the terminal voltage plus IRA plus IXL is equal to E, or the load-induced EMF. Sum of the terminal voltage plus IRA plus IXS is equal to no load voltage. Okay? So, makita ito pay nga ti IZ is equal to IRA plus IXL. IZS is equal to the sum of IRA plus IXS. So, surutan nyo lang dito yung vector diagram na. For the lagging power factor, this is your terminal voltage as our reference. For lagging power factor, we have a load power factor angle which is phi. And in lagging power factor, our current lags behind the voltage by a certain degree. So this is our I, and the drop in our resistance, armature resistance, is in phase with the current kasi lagging nga. Lagging. So 90 degrees with respect to IRA is our IXL and IXA. The sum of IXL and IXA is IXS. So papada da lang ti nagdiferensyaan da lang ketay angle or the unity lagging and leading. So dito naman our current leads the voltage by a certain power factor because our load here is leading power factor. So current natin leading dito with respect to voltage, kaya nandito yung IRA natin. This I here, nandito rin yung IRA, and then 90 degrees dito. IXL plus IXA is equal to IXS. Terminal voltage plus IRA plus IXS is equal to no load voltage. So, ang kay matiktikaw, surutan nyo lang dito yung vector diagram. IZ is equal to the sum of IRA plus IXL. IZS is IRA plus IXS. Okay? So, the induced EMF is equal to terminal voltage plus IRA plus IXL is equal to E. So, we will have an example. Example number 1. A three-phase star-connected alternator supplies a load of 10 megawatts at power factor equal to 0.85 lagging and at 11 kilovolt terminal voltage. Its resistance is 0.1 ohm per phase and synchronous reactance 0.66 ohm per phase. Calculate the line value of EMF generated. So this is a star connected. In your discussion in polyphase, when you have star connected winding or alternator, the E line is equal to square root of 3 E phase, and your line current is equal to phase current. Okay? So we have here a load of 10 megawatts. So PL, that is in 3-phase, 10 megawatts. And the power factor equal to 0.85 lagging. Terminal voltage VT is equal to 11 kV. Its resistance per phase 0.1 and synchronous reactance. Synchronous reactance is equal to 0.66 ohm per phase, or XS, synchronous reactance. Let's draw the vector diagram of this problem. Since this is a lagging power factor, we know that current lags the voltage by your power factor. So this is our terminal voltage and our total current. In between the total voltage and total current is your power factor, theta. Then your drop in the resistance, it is in phase with this current. This is IRA. And the drop in your IXS, a while ago we said that XS is equal to the sum of your XL plus XA. So this is now your XS, 90 degrees with respect to the voltage. So as you can see here, it is lagging with respect to our voltage kasi it is an inductive. So this is IXS. The sum of terminal voltage plus drop in RA and drop in IX is equal to your no load voltage. Calculate the line value of the EMF. Our line voltage is square root of 3 E phase. So in Y, IL is equal to I phase. How will we compute the line value of the EMF generated or the no load voltage? So from our formula, load power is equal to the square root of 3 E line, I line, cosine theta. So recall your formulas in circuits 2. Solving IL, which is equal to I phase in Y connected, that is equal to PL divided by square root of 3 EL cosine theta. PL is equal to load power 10 megawatts. 10 times 10 raised to 6 divided by square root of 3. EL is 11 kV. Times our cosine theta is the power factor 0.85, 0.8. Our line current will be equal to, that is 0.85. $617.487 amperes. Okay. So what will be the angle of your line current? So it is the arc cosine of your power factor. So arc cosine theta or arc cosine of 0.85 is equal to cosine 31.788 degrees. So the magnitude and direction of this vector, this one, is equal to 617.487 angle of negative, because it is red clockwise direction, or it is a lagging power factor, so that's why it is negative 31.788. We can use this one in calculating your IRA, the drop in IRA and IXS, because the current here, I, is the same to our total current. Okay, so we will now solve the drop IRA and IXS. IRA drop, so that is, let's say, VA for IRA. This is a resistive, so it has an angle 0. 617.487 angle negative 31.788 times the armature resistance equal to 0.1. That is equal now to 61.749 angle negative 31.788 volts. For the IXS drop, you will have, let's say this is VS for synchronous, IXS, that is equal to 617.487 angle negative 31.788 multiplied by J, positive J for inductive, multiplied by XS is, what is the value of XS? 0.66 ohm per phase. Don't forget the J operator. So that is equal to 407.541 angle 58.212 volts. EO now is the sum of terminal voltage plus the drop in armature current, or in armature resistance, I mean, and this one VS. VA plus VS. Vectorially. Add them vectorially. So terminal voltage is our reference, and we will use the per phase voltage. So we will divide the 11 kV divided by square root of 3 angle 0, because it is at the reference, plus VA. The value of VA is 61.749 angle negative 31.788 plus 407.541, angle 58.212. So our EO is in per phase. Kasi naka-per phase yung terminal voltage. That is equal now to 61.749. 6625.463, angle 2.715 degrees volts. The required in our problem is the line-to-line voltage at the no load. So EO line is equal to square root of 3 times 6,625.463, angle 2.715. That is equal to 11,475.638, angle 2.715 degrees volts. So the angle 2 is here. Ito. This is angle 2.715. And this EO here line will be equal to 11475.638 volts.